Hey, good morning, everybody. So, we've had a load of talks about the measurement of the magnetic field and the missions and the great science that goes on behind it. But realistically, society just wants one thing from us, which is a nice magnetic field map. And the rest is just detail as far as them. But it's nice that they fund such great instruments to do that. So how do we contribute to society, I suppose, is what I'm going to talk about here. And of course, this is to big magnetic field models such as the International Geomagnetic Reference Field or the World Magnetic Model. And they are big international collaboration efforts. And I was lucky enough to lead the last one, which is the IGRF 14. So this is myself and Clemens' work, and then all the work from all the evaluation panel, and all the people in this room have at some level contributed to this model. So thank you very much. Okay, so yeah, the majority of the human race don't care about the magnetic fields. In fact, probably don't even know it exists, but they do use it inherently every day of their lives without realizing. And of course, originally the magnetic field was measured and tried to be understood for navigation purposes, and it still is today, with declination being the angle between true north and magnetic north. And because all maps are usually aligned to true north, then you need a correction to understand the direction that you're pointing in relative to the compass direction at your location. So in the olden days, that was literally a compass, and of course ship's compasses were vital. But nowadays, everyone's got a smartphone, and even people who don't know about magnetic fields use it when they're looking for their Pokemon characters in their virtual reality landscape. So with that, just as a background, people have been trying to understand the magnetic field for certainly hundreds of years, maybe even longer. And one of the earliest attempts was by Halley, who spent 2 years tracking around the Atlantic Ocean, measuring the declination angle to make this map, which is the first map of the magnetic fields that we know of. And I think there's a copy upstairs, actually. If we were to go ask the librarian, they could probably dig it out for us. This is also one of the first maps to use contours to show that the lines of equal value across a spatial area. And of course, during the trip, Halley realized that actually the magnetic field was changing constantly and in a non-linear way. So he realized that actually the maps would not be useful for determining longitude, which was his original purpose. If you jump forward a few hundred years, we've got a plot on the right-hand side there showing the declination change over the last 120 years or so, as measured in the UK, starting in the Greenwich Observatory, which is a few miles up the river here, and then being picked up by the other observatories, Hartland, Eskdalemuir, and Lerwick, which were established because London became too magnetically noisy. But you can see there that the rate of variation is constantly changing, up and down, and it's not at the moment possible to predict it. So therefore, we must measure it and make maps of that to continue. And we were talking yesterday in our workshop about jerks, and the famous 1969 jerk is there very, very evidently. And then there's been some smaller variations as we get better and better measurements in the last decades. Okay, so the International Geomagnetic Reference Field is then a large-scale map, a global effort to try and make something that is useful for the public and to justify our salaries most of the time. So it's a very formal process. It's created under the auspices of the International Association for Geomagnetism and Aeronomy, and that itself is part of the International Union of Geophysics and Geodesy, or Geodesy and Geophysics. And then that itself is part of UNESCO. So it's all flows down from the UN and has that sort of very formal UN feel to it, with committees and workforces and tasks and all that. So in the last iteration, the 14th generation, there had been 13 before that. It was originally started back in the 1960s as a collaboration between some of our more famous forefathers. And over the years, it's been updated every 5 or 10 years, within between 2003, for example, was an update because we had better satellite data. So it's sort of settled on a 5-year update schedule, but can change. It's not set in stone. The idea is that forms a committee, myself and Clemens, and then we sort of establish the ordering in which we ask for teams to form. We ask for volunteers for an evaluation panel. We ask everybody to contribute by October of the previous 5-year endpoint, and then we release the model in December of that year, and this is 2024. And it's represented as spherical harmonic fields up to the green order 13, and here's some of the coefficients just in that table on the right. And we ask for two main field models in 2020, 2025, and then a prediction for the next 5 years to 2030. And then when it's released in January, it's valid for 5 full years. And in this last iteration, we now have included Swarm and MSS data using nearly all the models, and then one model had CSS data in it as well. So it's now a global international effort, and all the satellites we have, and we will have in future, hopefully, will contribute to making this. Okay, so this was a record year. We had 19 teams this year. We had 47 different candidates, and we had a record number of researchers involved, so 85 or roughly 85 as last count. The table shows you a little X where somebody's contributed a model and a dash where they didn't contribute a model. So most teams contributed to most of the 2020 model, which is the DGRF, the 2025 model, which is the IGRF, and then the secular variation. Now, with that number of models, in the past, it was all done by email, and so you'd have V1, V2, and so on in your inbox, and there would be a lot of going back and forward, and quite easy to sort of make mistakes or get the wrong model. So with the help of Ashley Smith and Clemens, we set up what's known as a GitHub repository, which is an online method of collecting data and running code automatically. And in this case, we set it up to generate comparisons between the models relatively easily. The idea is it's open access. Anybody can go away and recreate this, and it's part of the FAIR principles, which is findable, accessible, interoperable, and reproducible, or something like that, or something that goes like that. And everybody's free to go and look at the GitHub repository, download the evaluation themselves, and run it to their own heart's content. So this is what the GitHub repository looked like, and what we asked the teams was to upload their model to the GitHub repository, and then they can then do an automated comparison to all the other models, or they can download the repository, run it on their own computer, check their model works okay, and then upload it separately. Or people could email it to me if they really wanted to, and then I would do that for them. So we created this automatic website. Ashley set up a lovely job. So you could go to this iaga-vmod github.io, and you could see the models being submitted and then updated more or less in real time as they went along. So that was a really nice innovation. It meant that it took away a lot of the work that was required later on for comparisons. So this is something like the plots that were generated. There are some standard ways of checking these things. You look at the root mean square differences between the models and so on, and you can plot them out as a sort of a square or a half square triangle plot showing the differences between the models. So for example, the BGS model was 10.7 nanotesla root mean square difference with CSS, and a little bit less 5 with DTU, and so on and so forth. So that was a kind of quick visual comparison. And then you could look in detail at spatial maps to show how the different models were different from each other. And this is a comparison between the median of all those candidates and each individual candidate. You can see some have different structures and some have very little structure. Normally there's some sort of hemispherical bias that appears. So this allowed the task force who were doing the evaluation to understand which models were different and why, and whether that was a problem or not. So for the IGRF candidates, you can see that, again, they're quite similar to each other. One candidate stood out because it wasn't made using satellite data, it was made using observatory data. That's the Strasbourg model, and that's why it tends to look a little bit different. And again, another way of looking at the model differences are via these triangle plots of coefficients. So this is just how different each coefficient is from each other. And sometimes you can see that there's some structure along the order 0, which would be a zonal difference, or there might be structure along, for example, the sectorial terms. And or in the case of the Strasbourg model, all the terms are quite different from the consensus models, which are all built out of satellite data in the other cases. Okay, so the task force had time to go away and look at all the different models, apply their own tests if they wished, and then at the end we had just a democratic vote. So what was your favorite way to combine things? So with the DGRF, all the models were very, very close to each other. There really wasn't much difference between them. So we voted to take the median of all the candidate coefficients just because it's an easy thing to compute. In the other two cases, the models were more spread, the differences were larger between them, so we opted to do what was called a Huber-weighted mean in space, which is where you effectively turn all of the models into spatial maps, and then you sort of effectively weight them in Huber space spatially, and then you convert it all back to spherical harmonics. And that way everybody's model contributes in some meaningful manner to the overall final model. Then it was released on the NOAA webpage, and Ashley also set up a Zenoda repository, which is the CERN data repository, and we uploaded everything onto GitHub. So now it's free and open for everybody to go back, check what was done, recreate it themselves, and then the candidates will be hopefully available for many years in the future for everybody to go back and check. Okay, so just some quick results. Hopefully everyone's well aware of what the magnetic field looks like. So we've got declination maps here. The dotted line shows the agonic line where declination is 0. You can see blue is where it's pointing west of true north, and red is where it's pointing east of true north. And in the inclination, you can see the effect of the South Atlantic anomaly. And then in the total field at the bottom, you can see the strength of the magnetic field. You've got these effectively two large lobes in the northern hemisphere. You've got the large southern hemisphere lobe, and then you've got the South Atlantic anomaly sitting quite obviously there. And then the rate of change looks a bit different because you're looking at how things are moving. And then you still got this kind of strong westward drift over the the Atlantic hemisphere, and very little relative change over the Pacific hemisphere. Okay, the public outreach for this, I did a lot of press around the time, as did Will as well. You might have seen me, heard me on the radio in Britain. I was on the radio 3 or 4 times. Couldn't get enough of me. But what they're really interested in is like, the magnetic North Pole moves, and you're like, yes, it does. And it's a little bit like people have a goldfish memory. Every 5 years, people go, what? The magnetic field moves? And you're like, yes, that's why we update the maps. You know? And then is there any kind of like problems with, I don't know, satellites or whatever, the usual kind of inquiries you get. GPS, was my GPS going to fail? No, it's not related really, but it's part of the system. So you can see that the North Pole continues to now move towards Siberia. The magnetic South Pole is drifting offshore. The red dots, sorry, are the dip poles where the field dips at 90 degrees into the ground. The blue dots are effectively the equivalent, just dipole version of that. And the rate of change of this pole, North Pole in particular, moving has slowed down rapidly over the last few years. We got caught out several times by underestimating this in the past. So, but it is slowing down, and it slowly still continues to move towards Siberia, but not at the same rate as it did 20 years ago. Okay, how good are the candidates, and how often do we? Why do we update this every 5 years? Well, the answer is because the rate of change at any given observatory is quite unpredictable, particularly given these geomagnetic jerks, for example. So here's the sort of a plot of Vesuras Observatory in Brazil, which is near the South Atlantic anomaly, which is why I picked this one. And you can see that the candidate models are just shown as those various dotted lines right towards the end, from 2025 to 2030. And there is a fair amount of spread, but you can see within the secular variation in the X, Y, and Z, there's also a fair amount of spread over time anyway. So which one of these models will be right in 5 years' time? Well, we'll find that out. And then whoever is the winner gets a round of applause at an IAGA meeting or something like that. So there's no prize really, but just you get the glory, you know, get the honor. Another way to look at this is at the core mantle boundary, just looking at where the radial field is 0, and each of these models sort of shown for 2020, so you can see the models are quite closely overlapping. There's some kind of difference near the Caribbean, that's the main difference as far as I can tell. And then for the 2025 models, you start to see a little bit more variation. And in some of these models, the reversed null patch in the southern hemisphere is actually starting to combine together to become even larger, just where I've shown the arrows there. So these patches probably will merge by 2030 in the next few years. Okay, just other points of interest for the general public. The lowest point of the field is, for this particular model, it can change depending on what model you use, is over Argentina. It's roughly 22,070 nanotesla. That second point over South Africa, or just off west of South Africa, continues to deepen. And so the South Atlantic anomaly is still growing larger. The North Dip Pole and the South Dip Pole will actually briefly coincide in longitude right about this time, actually, roughly about March 2026. So they're both at minus or 136 east, which is probably hasn't happened before, or certainly not in the last few hundred years. And then these bursts of secular variation in the Pacific and East Indian Ocean are still ongoing, and actually they're typically the regions of the largest misfit in the model. Okay, so just to summarize, you've all contributed to producing this map, and the public thanks you. It's freely available for everyone to use, gets embedded in all kinds of systems that we probably don't even know about. One thing that we haven't really cracked in the last 20 years, despite having all this great satellite data, is that our prediction by the end of the 5 years really hasn't changed in the last 4 generations. So maybe that's something we can work on with all this new data. Maybe there are new techniques. Maybe it's not a data problem, it's a technique problem. So, for example, physically informed neural networks or machine learning techniques might come into the fore. There's a special issue that is almost complete. We're just waiting for the last 2 papers to be approved, and then we should hopefully get finally the official IGRF 14 paper so that you can all cite it in your next papers and make sure that everybody gets a great citation number on their record. And finally, yeah, looking forward for IGRF 15. That won't be me, that'll be Clemens, I guess. So good luck, Clemens. But we'll have a plethora of data, hopefully. We've seen some of the new satellite missions coming through. And so it will be a case of what data to pick rather than not having any data at all. So thank you.